Hi everyone, Dr. Matecki back here to talk about our Solow growth model spreadsheet. You can find this on D2L in the learning materials. I want to focus on the second and third tabs in the spreadsheet. So we already talked about the first one. And the second and third tabs build on the initial model to incorporate the material in Chapter 9. So it incorporates population growth in the second tab, and in the third tab down here with population growth and technology growth. So this can be used to solve problems. If you have a problem and you're given a bunch of parameters, like you see here with the the production function parameter, the savings rate, depreciation rate. If you have all of that stuff, you can use a spreadsheet to solve for the steady state values of capital, output, consumption, investment, etc. And so again, the way to find those is to first input all of your parameters up in the gray box, and then go down to the end of the simulation here. So there are actually 231 lines in this spreadsheet, but I have most of them hidden. So if you look down here, and after 220 time periods, you can see that the values have stopped changing. The delta K, the change in the capital per worker has gone to 0, so the capital stock is not changing. Capital per worker is not changing. So that means all of these other variables are going to be constant as well. So once we've reached this point where delta K is equal to 0, we know we are in steady state. So one of the interesting things that I want to point out is that just because our capital per worker and output per worker, etc., are not changing in steady state, our aggregate variables, so like the capital stock, the number of workers, total output, which we would measure as GDP in the economy, these things that we frequently observe in the economy, these things are changing. And so these should match up with that chart in the lecture. So you should see that the growth rates that we've calculated here in the last two columns match up with that very important chart that I'd like you to be able to interpret. So if you haven't looked at that lecture notes video, take a look at that the last 5 minutes or so. If you can understand that chart, then you're well on your way to understanding the logic of the Solow model. So we can do a couple of experiments here to see what's going to happen. But before we do that, I'd just like to point out that, so even in steady state, the aggregate capital stock, so not capital per worker, the aggregate capital stock is in fact growing every time period. And if we look in column L here, I've calculated the percent change. So this is just looking at the percent change of this column here. And so we can see that initially the capital stock is growing more rapidly, and then it tapers off, and then eventually settles in a steady state on a growth rate of 2%. So notice 2% was the growth rate of the population up here in our parameter box. So the capital stock is growing at the same rate as the population. The same is true of aggregate output, big Y here. So again, initially it's growing more quickly, but then settles on a growth rate of 2%, which is equal to the population growth rate. So even in steady state, the output and capital stock are both growing at the population growth rate N. So it's also interesting to note that we're talking about a long time period here. This is 220 periods, but just look at the growth in GDP. So we started off with a GDP of 86.6, and now we're up here at 9,557. So tremendous growth in GDP over this time period, when really we have pretty small figures here. So population growth rate. We can also run some experiments to see what happens when our population growth rate changes. So right now it's set to 2%. So what happens if we were to change this to, say, 3%? So now think about your Solow graph, and so this would cause that break-even investment line to shift up, sort of rotate to the left. So an increase in the population growth rate should cause the steady state value of capital per worker to decrease. So let's see if that actually happens. Let's change this from 0.02 to 0.04, so 4%. So we can indeed see that is the case here. So steady state capital per worker is now down to 4.592. And so again, no matter what we do with these initial values of capital per worker, which drives all the rest of these values, whatever we do with this value here, it's not going to impact the ultimate steady state value. if instead we were to decrease the population growth rate to 1%, so we could input 0.01 here, we can see that the steady state capital stock per worker has increased. So now notice also down here the growth rate of output and the growth rate of the capital stock, the aggregate capital stock, has adjusted as well. It's now growing at 1% in steady state, the same rate as the population growth rate. All right, so one big lesson to point out here, though, is that even though we have population growth, our output per worker and our consumption per worker are not changing. So remember, how we measure the standard of living in an economy is generally per capita GDP, or you could look at consumption per capita as well as a measure. Those two measures are both constant in steady state. So for many years, these things are going to be increasing as the economy approaches steady state. So we do have change in the standard of living for a period of time, but eventually those changes diminish and we end up stagnating at the steady state level. So if we're going to make our model match the data that we actually see, which is essentially perpetual growth in the standard of living, then we need another factor, and that's where technological change comes into play. So if we look at the next tab, including technology, so we have the same parameters over here, but now we have to specify a few different things. So even in the previous tab, we had to specify an initial labor supply. So we have that set at 50. But now we have to also specify the growth rate of technology, G. So I currently have it set to 0.06 for 6%. And we have to also specify the initial E to get our first period values here. So again, you can play around with any of these parameters and see how the model changes, and you go down to the end and see what happens to the steady state. So remember, the steady state now here is per effective worker, in per effective worker terms. So in steady state, per effective capital, output, consumption, investment, these are all going to be constant. However, the story is going to change when we start looking at some of these other variables. So now look at what happens to aggregate output over time. So again, this is like the equivalent would be GDP if we were looking at collecting data to measure this. So you can see that GDP has now grown from 86.6 to about 2,219,426. It's grown a lot, right? So even in steady state, right now we are growing at approximately 8.1%. And so where does that figure come from? So this is an approximation. So the 0.1 is off a little bit, but essentially this is going to be the growth rate of technology plus the growth rate of population. That's what output is going to grow at. So we can also look and see what's going to happen to output per worker in this scenario. So now output per worker is no longer constant in steady state. So output per worker is growing at 6%, which is the rate of technological change. So standard of living increase, you think, a little bit here. So we started off at 1.73, and then after 220 periods, that has turned into 580,541. So that's quite a growth rate. So you can see the power of compounding growth. Now, technological change, that's a pretty hefty growth rate for this sort of model, so that's probably not realistic, but you can see the power of compounding growth. And so you can see that, I didn't do this on the other tab, but if you were to change the initial value of L or E or anything like that, you can sort of see some interesting results here. So let's see if we change this from 50 to 100. Okay. What happens to our steady state values? So pay attention down here. So when I click the change, you'll notice that the steady state values don't change at all. Okay, so what does change? Well, we now have a bigger population that's producing output, so our GDP has grown quite a bit. So it's about twice as big as it was before. And the output per worker, though, has remained the same. So even though we have a bigger economy, each individual person is about the same well-off materially. So once we increase the population, so we just essentially have a bigger economy, but the status of each individual within that economy has not changed. So again, I encourage you to open this up, play around with some of these parameters, make a prediction about what you think is going to happen. So what do you think is going to happen to the steady state if you change the savings rate or depreciation, the initial level of capital, all of these things. You should be able to tell me what's going to happen to the model variables when any of these things change. And again, this is great for solving problems and also getting intuition. So also make sure to look at the notes I've put here. So if you have any trouble interpreting what's going on in these cells, so look at the notes. I explain what I'm doing in each column. And then you can also dive into the cells here to see the formulas that I've input. That'll also help you sort of understand where these values are coming from. You can just. So that wraps up what I wanted to say about the Solow model in this spreadsheet. So if you have any questions, please let me know. I'm happy to go over any of this stuff in more detail. Just reach out, let me know. Thank you.